So hello everyone, welcome to my new video. In this video, I'll be discussing about the Butterworth Van Dyke model, or abbreviated as BVD model. So I will first give an introduction on what is a BVD model, and then I will take two examples of a one port resonator and a two port resonator, and show how you can draw a BVD model of that. So now, yeah, just now let's get started with that. So BVD model is a model for modeling of resonators. So what is a resonator? Resonator is something which is like mainly is something which we call in a, like when you are applying an electric signal, you're able to generate a vibration or something. So then what you're doing? Then you're actually using it as a you're you're actuating something. So if you're actuating that, and then if you're using it as also sensing that thing, so resonator as you can say both as an actuator and a sensor. So that's what happens. So that's the basic idea of resonator. So yeah, you can actually read up on what is a resonators and stuff. So now we can actually continue to our video, which is BVD model. And next thing, so what is this BVD model doing? So you will have first this Fs is the force, m is mass, x is displacement, and b is the damping. So x double dot is acceleration. So this you know, right? So this is the basic equation of a force equation. So the electrical equivalent of that is, so electrical equivalent of force is voltage. So electrical equivalent of mass is inductance. Of damping is resistance, and of our spring constant is capacitance. So this is the electrical equivalent. So ultimately what you're doing, so this is a motion. So resonator is in motion. So in the motion, you are actually modeling it in the electrical, you're modeling it as an electrical circuit. So that's the idea. What is the BVD model basic idea? So you need to know what is the equivalent in the mechanical domain. You need to know what is the equivalent of that in the electrical domain. So that is the thing. And in that, so so there is one very important thing called the piezoelectric transition coefficient. This piezoelectric transition coefficient relates this the electrical and the mechanical domain. Okay, so when I'm saying in the mechanical domain, so I can't model like in an electrical domain. What we only have resistor, component, inductor, capacitance, those things, right? So I can't put mass, damping factor, and what is a spring constant in that and model the same as electrical circuit. So for that, there should be something which is converting it from a mechanical domain to a electrical domain, and that factor which helps us, or that constant factor which helps us in converting, is this piezoelectric transition coefficient. Okay, so that's the idea. So, so this piezoelectric transition coefficient eta is equal to F by V, or it's also equal to Q by X. Q, is the charge and X is the displacement. So what is this? So if I apply a voltage, I will produce a force. Okay, so this is all about piezoelectric. Okay, this is a piezoelectric material. If you apply a voltage, you are generating a vibration that you can call it as a force. It depends on how you use it. So that is actually called indirect piezoelectric effect. So Q by X. So if you are applying a displacement, is generating a charge. That is your strain is producing a charge, and ultimately that charge separation is what is generating electricity, or yeah, that is what is, or voltage, you can say. So so Q by X, you can call it as a direct piezoelectric. Direct piezoelectric, that is with displacement you're generating charge. Indirect piezoelectric is it with voltage you're generating force, or you can go like with voltage you're generating a strain. Okay, that's the idea. So that is these two equations basically mean. And then, so I told that in mechanical domain you're converting it into electrical domain, right? So this is related by the piezo transition coefficient. For M effective is given by Lm by eta square, B is given by Rm by eta square, and K effective is equal to eta square by Cm. So can take it as K effective inverse. So that brings us to our PVD model, which you can say that this part is actually So if you don't have any motion, then how do you model a usual material? So you will have a capacitor, you'll have a resistor and stuff, right? So this is that part of the, this side is that part of the only you're considering without a motion. So even if you don't have motion, this will always be there in your modeling part. And and if you have a motion to that, so that is what, so this part is called the transformer. Okay, so you're transforming your, what do you call, your motional part, you're transforming it into a electrical component part. So your B, you are actually making it a RM. How? By this formula. First of all, you need to know what is eta preserved transition coefficient. So yeah, that you can find out using this formula, or you can also read upon that, more on that, if you want to know more on that. And so CF, from the K effective, you will get CM by dividing by eta square. You actually are getting K effective inverse, and then LM also you get from the M effective. If you have M effective, you can find LM. So ultimately, what you have done, you have ultimately made a electrical circuit using the things, or using the mechanical domain terms, M effective, B, and K effective. So that's how, so that's basically the idea here. And next, I'll show you how you can make a PVD model of a one port resonator. So you have a one part, like you have ground here, you have a top part you're applying, so basically you're giving a voltage difference between these two. So this blue thing is the top electrode, and this is the green is the bottom electrode, and this um, red part is the piezoelectric material. So that is how you are producing a strain. So here, what here is actually, with a voltage you're producing a strain. That's what's happening. So here I'm driving it. So that's why I'm, so BVD mode, this is the equivalent BVD circuit. So I can just explain on the circuit. So you'll have a ground. So this is the ground part. So here, and between the ground, there is an AC signal I'm applying, right? So it's like this part is, so from here I am actually giving, so there's a ground here, it'll be here, and I'm giving an AC. It's on top, on the top electrode, and there will be a resistance of the electrode, that is the RS. So as the R is the resistance of the top electrode, and then there is a motional arm, right? This is the, so you have a, because of the, so I've already explained in the last slide how what these are. So basically you will have all these things coming, and finally attaching all these things coming in the piezoelectric material, and then attaching all of that to a ground. And so similarly, uh, and parallel to that, what you will have a capacitance. C0 is the capacitance between these two electrodes, that is the top electrode and the bottom electrode. So you can, so capacitance is equal to what, epsilon zero A by D, right? So epsilon zero is the uh, permittivity of free space, and A is the area of the electrode. So you can actually think of this part electrode. So till where, so yeah, you can basically understand, like, so you have two parallel plate capacitors, and it's actually epsilon zero epsilon r A by D. So you also need to look at the relative permeability of the piezoelectric material. So for example, if you have a AL material is 10, and for a PCD it will be 1000, or yeah, like that, you can basically look onto that. And then, so between these two electrodes there will be capacitance, that is C0, and R0 is the dielectric resistance of the material. So yeah, that's how you can draw a BVD model of a one port resonator. So this thing you can actually uh, put in your ADS software, or yeah, or any other software, I don't know other software. So in those softwares you can actually put this, and then simulate your, so you will be getting an experimental results, like some, like parameters called S11 Y11. So admittance, so S is equal to what, it's actually 20 log V1 V out by V input, or you can call like power output by power input. Okay, so yeah, so I'm just saying, like, parameters like S11 S22. So S22 or S12. So here you will have, since it is a one port, you will have only S11. So S11, I'm saying like those 11 means actually the first one means the output and second one means the input terminal. So basically that, so you will be knowing all those stuff. So ultimately, so with this circuit you can actually check whether your experimental and your this where your circuit is matching. So yeah, it's just a modeling of the circuit. And second I'll be is the two port resonator. So here also everything is similar except that you will have what is here, you are actually using this port, like port 1 you are using to give a voltage, you have a ground here, and here you are using port 2 as the sensing part. Okay, there you will have, yeah, this is so this is the actually the resistance of the electrode. Bottom electrode, you can like what's not bottom electrode, like the top electrode is blue and bottom electrode is still green. Okay, sorry for that. Yeah, so and your bottom electrode is then connected to ground. Yeah, similar to one port, but yeah, here you have actually between the two electrodes there is a gap. So yeah, ultimately making it a two port. So this port you're using for driving and this port you're using for sensing. So here in a one port resonator you're using the same one port for driving and sensing. That's why I call it say S11. You'll get only S11 parameter. It is 11, yeah, same thing. So like you're driving in the same port and you're sensing in the same port. So here what you're doing, you're driving in port 1, you're sensing in port 2. So here in the port 1 itself you will have a capacitance that is C01 between the two, like this blue part and this green part. Here your area will be the like up only the this electrode, so it will be from here to here. Yeah, and then similarly you have distance will be distance will be the actual thickness of the piezoelectric material. So from that you will get C01, which is the capacitance of the due to the first like the driving electrode, and then you have capacitance of the sensing electrode, that is C02. And so similarly the same thing you will have the RM, CM, and LM produced due to the motion. It's called the motion law. And then you have a CF. What is CF? CF is the capacitance between the, so this is also acting as a parallel capacitor, right? So you can imagine either it is will be if it is a, if this resonator is in vacuum, then you can take it like perfect epsilon zero. You can, or you will have to, or I think epsilon relative permittivity of air is also, I think it is one. I'm not sure. Like yeah, if it is one, then you can actually take epsilon zero, epsilon r a by d. So so A is now this surface. So this like you can think it of like the thickness of the uh, electrode into how much width is there in the electrode. Like in the, you can think it of is the direction inside the plane. Okay, so yeah, it's going inside. So basically yeah, you understood, right? So this is the electrode. So the capacitance between these electrodes is CF. So so that is the CF. Uh, so 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 ultimately this is the whole thing. So and finally this part also I have already explained, C02 you are connecting that. So it will be like this part, and then you have a piezoelectric material which is the motion arm, and then all of that is then connected to a port 2 which is sensing. And yeah, so this is all in the video. So please subscribe to my channel if you like the video. And yeah, you can also add, put comments on or on what all, if I have to improve anything, or if I need to, or if you want me to make a new video, or if you need more explanation on some part. So yeah, please do comment on that. Yeah, thank you.